Okay. Oh, there's a pre-question on our live stream about asking whether the things we're talking about in the last live stream, are these things all available in the free online version? Everything that exists in the, I mean, some of the things we're talking about are things we're going to be building in the future, but things that I was running there were all things that are available because that was all I could run, because the things that haven't been built can't be run yet. So yes, the answer is yes. Okay, what we're going to be talking about here is our quantum computing framework. There's a certain poetic something to this that in our project to find the fundamental theory of physics, which has been sort of activated again after decades of hibernation, we finally actually think we understand what quantum mechanics really is, and it is sort of ironic that we're now producing this quantum computing framework right at the time when we think we actually understand how this works underneath. But that's all just amusing. All right, let's see. I said run all code. Is that, yeah. Okay. All right, so let's get going here. Okay, let's get a sense of what's going to happen here. Oh boy. Okay.
There are some other things that aren't in that document that we also should discuss at some point.
Okay, let's start off here. So first question is, do we believe that we are more or less code complete to put out this package? Is that a true statement or is that not a true statement yet?
It will be a true statement very soon. So, I mean, the modulo 2 functions that we still want to add, which are quantum channel and quantum compile. Both, I mean, a quantum channel is fairly straightforward. Quantum compile has some difficulties associated with it that we'll discuss later. But other than those two, I think, yeah, everything else is code, will be code complete very soon. And so then it's basically design problems we have to figure out.
By the way, an absolutely pedantic point here, we don't put periods at the end of these descriptions and guide pages.
Okay, I'll take a note of that.
Okay, so, okay, here's a weird question for you, Jonathan. Do these things actually dovetail properly with the way that we're doing quantum stuff in the physics project? Like
yes.
Quantum entangled Q?
Yes.
Is it all going to just work?
It will. So okay. Without us getting too far off track into this stuff, I have actually worked on writing a few converter functions between multi-way system and the quantum framework, which I can show you later. But
exciting.
Which basically do that.
Okay, somebody's asking on our live stream, what new development made us understand quantum mechanics? A big project that we've been doing that we were hoping to announce right around now until the world shut down, but hopefully we will be able to announce in a few weeks. And Andre on our live stream is asking, shouldn't this framework be deployed on an actual quantum computer? Yes, we hope to make those connections, but first we're just trying to get an emulator.
Well, I mean, that's the purpose of this quantum compile function, right? So,
okay.
So the idea with quantum, okay, we'll discuss this in more detail later. But the idea with quantum compile, and Ruhi has a prototype version of this working, is that it will take an arbitrary operator or circuit and a gate set, like for a real quantum computer like the IBM Q, and it will decompose that circuit or operator into compositions of the gates in that gate set. And so then that's then a representation we can send off to an actual quantum computer. It gets a bit complex because then there are some external dependencies and things, and we don't quite know how to handle that yet. But
so wait a minute, the gate sets are published specs for each of the companies that claim to have a quantum computer. Is that correct?
Exactly. So company X will say, "I built this quantum computer, and it uses CNOT gates and Hadamard gates or something." And so then we then have to we have a fancy matrix factorization thing that will take any of our circuits and decompose it up to some arbitrary precision into a composition of CNOT and Hadamard gates, which we can then send to that computer.
Fine. By the way, I mean, we should be making sort of preliminary versions of this package available to people soon. We have to figure out how to do that.
Right. Yeah, there were some text services issues because there were a bunch of people contacting text services about that, and we weren't sure exactly how that works with NDAs and things.
I don't think we need NDAs for this. I mean, there's just a package that's going to be available anyway soon.
Right.
I mean, I think we should just make it available. I just don't know what the right mechanism is. And I mean, as soon as the public Packlet repository is available, this would be an obvious thing to put in there. And maybe we can, now that in 12.1, now that the Packlet system is user accessible there, we can just publish as a Packlet and describe it, through the community or whatever else for now. Okay, let's dive into to content here. Every discrete operator, measurement operator, now automatically has a quantum basis object associated with it. Okay, so wait a minute. So this is a quantum discrete state. A pure state. Does anybody really use this term qubits? Is that really used?
I've seen it used. I mean, I think we discussed at one point whether to call it qubits or whether to call it subsystems. And I think we decided, because the main emphasis, at least initially, is on quantum computing, that we should call it qubits. But I'm also not against calling it subsystems.
I think that's even more obscure. I mean, whatever. Okay.
What do we call it then?
Qubits. I mean, I don't think the number of non-binary qubits is not large, is it?
Well, but the point is, we want this framework to support, discrete state quantum mechanics, where you have more than two levels, and then it's no longer a qubit. Then it's a qubit or a subsystem.
What, but do people call them qubits in discrete quantum mechanics nowadays?
Again, I've certainly seen it I've seen it used in that context. I don't know how common it is.
Okay, somebody here on the live stream says, coming from physics, they've never heard the term qubits.
Maybe it's a math thing.
I think we should consider what we want to call that. Let me think for a second about that. I mean, what does it really represent? It's telling you how many n-level quantum systems are part of this quantum discrete state.
Exactly.
So, well, the question for our live stream, if anybody knows a better generic term for that covers both the physics use and the quantum information use. All right, okay, so this is a basis here. All right, basis element association. Okay, oh boy, that's kind of interesting looking. The kets and the associations hanging out together.
It is a bit weird, yeah.
It's okay. Okay, so that is our representation. Ket of 0 is 1, 0. Okay, so that is the representation of the basis as a vector. Correct? And that's the name of the basis element is ket 0.
Right. So if you remember, our design for discrete state is that it's an internally all it is it's an association mapping basis elements onto amplitudes. And so this then gives a vector interpretation of those basis element names.
Okay. Okay. So then here we've got these direct products basically are represented in this way in this basis. Is that correct?
Exactly. So we assume everything is a qubit unless otherwise specified. So if you give it a four-dimensional vector, it will assume that it's a tensor product of two qubits, which is what it's doing here. But you can specify that it's actually a four-level quantum system, in which case it will automatically change the basis to the appropriate thing.
And these, by convention, are going to run from 0 to n-1.
Yes, that's the quantum information convention.
As opposed to spin systems, which would run from minus L to plus L or something.
Right, exactly. And I think so. Ruhi has been accumulating a bunch of these sort of commonly used bases, and I think she has been attempting to find out what the sort of standard notation for those is. What is the relationship between sort of angular momentum stuff and these bases? Well, I mean, the Clebsch-Gordon decomposition allows us to do effectively a decomposition of an arbitrary state vector into a basis or a tensor product of bases with angular momentum components. Okay,
do we have that Clebsch-Gordon decomposition?
I think Ruhi was working on it, but I don't think we have a version in this package.
Yeah, not yet, but it's a work in progress thing.
Okay.
We have a bunch of other.
The good news is we certainly have the Clebsch-Gordon coefficients. We've had them for 30 years, so you should be able to.
Yes, yeah, and there are very fast numerical algorithms for kind of decompositions over SUN and things. So it should be possible to do it quite efficiently. It's just we have a bunch of decompositions.
Why do we need SUN? I mean, I thought this was in real space.
the Clebsch-Gordon decomposition, well, for qubits is over SU2, and in general dimensions it's over SUN, is it not?
No, I thought it was over. No, I mean, isn't it just different representations of SO3 or the covering group of SO3?
Which up to double cover is related
SU2.
to. Yeah.
Right, but my point is, it's not SUN, it's just SU2. It's just, a spin 18 object. It's just an appropriate representation of SU2. Or in the case of a spin 18, it would still be a representation of SO3, but if it's spin 18 and a half, it's SU2. And I think that our existing Clebsch-Gordon code will efficiently handle any of those things. It's Clebsch-Gordon coefficients for, the existing Clebsch function, Clebsch-Gordon, that's the SO3 Clebsch-Gordon coefficient. Okay, so that's a decomposition of Jm in terms of J1, M1, J2, M2. So that should be exactly what we need.
Right.
We even have the symbolic forms of it and everything.
Yeah, the SU3 case is known analytically, but there is an SUN case, and that's known.
Okay, fine. Okay, but this one is known analytically, and it's known in terms of hypergeometric functions and so on.
Right.
There are some issues here about the conventions used for the Clebsch-Gordon coefficients, which we need to watch out for. That's something for Ruhi to figure out.
Right. These are some nice numerical algorithms for the general SUN case.
Okay. Which would be interesting to have for our, Clebsch-Gordon, the question there is, are we going to generalize the Clebsch-Gordon function to be a Clebsch-Gordon coefficient for an arbitrary Lie group?
Certainly an arbitrary special unitary group, I think, is worth doing.
Well, okay, that's interesting. That's that would be the first generalization of Clebsch-Gordon. When was this? This was in version 2 in 1991. So it's been around. It's a venerable function. Okay. Let's keep going. Most built-in bases are vector valued. Okay, so you are providing these symbolic names. What is that thing? What is that? Is that an X that's sitting in? Is that a string X? What is that?
Right now, that's a string X. But yeah,
okay.
Sorry, Ruhi.
Oh no, yeah, it's a string. Yeah.
I think that's okay.
We could also make it a formal X.
No, let's not do that. I think this is. I don't think you're going to be able to compute with these things. The only issue is if you have a spin 10 object, but then you should use, those things there are presumably, actual numbers, right? Yes, they are.
Right. And we do have versions where you have a string and then a concatenated number. You'll see those later on.
Okay, that's not the most lovely thing in the world, perhaps, but
right.
Okay. Why are those? If you're going to go stringy, why don't you actually have those be subs? What are these?
They were in Ruhi's implementation. This is my own mess up.
Okay. All right. So those are sigma sub 0 as a string is that element, and these are the Pauli matrices, right?
Exactly. Yeah.
Okay. Boy, I'll actually understand. I thought I understood this stuff 40 years ago, but I'll actually understand this stuff with us being able to implement it like this. So what the heck is that? Picture Schrodinger. Wait. Are these all? Okay, wait a minute. This is a state type pure. This is the Schrodinger picture basis. Do we have a Heisenberg picture version of these things?
We have Heisenberg interaction and phase space, as you'll see later on.
Wow. Okay. Cool. Okay, what is this? I don't know what the Schrodinger basis is. What is that?
Right. Okay. So the comma 2 there is telling you that it's that this is the Schrodinger basis on 2 qubits or 2 subsystems, whatever. So the Schrodinger basis is a rank 2 matrix basis, and so this is giving you the tensor product representation of that. So if you did Schrodinger comma 1, I think it would just do the standard Schrodinger basis for a single qubit.
Okay. All right, that's that basis. Quantum tensor product.
So it's just
Of
saying
the two, I see, of the two, Schwinger basis of rank 1 gives the Schwinger basis of rank 2.
yeah, exactly. Or in this case, the Pauli Y basis of rank. Yeah.
There's a question from Peter on our live stream asking, does it mean if I want to call out the vector, I need to type the full bracket form as the key in the association? Yes, if you want to get out the sigma 2 component here, you have to use that as the key, right?
Right now, yeah, we might want to write a shorthand for that.
I think it's very clear what's going on there, which helps. I mean, there's no mystery about that. Okay. Quantum discrete state. 1, 0 in the Pauli Y basis. Okay, so if I were to take this, and how am I going to show, what properties can I see for this?
What do you want to see? I mean, you can see the state vector, you can see the basis, you can see its amplitudes, whatever.
Well, the state vector was kind of boring, right? Because I just typed it in.
Right.
Let's see the amplitudes. What do I ask for there?
Amplitudes. This might do something weird. Yes, it is going to do something weird. So when I finished integrating Ruhi stuff into this framework, the amplitude, the keys for the amplitudes will be the same as the keys in the quantum basis object, but that isn't the case right now.
Okay. Quantum tensor product. Okay.
So that's just showing that if you take tensor products of qubits in certain bases, then the bases also get tensor producted by default. And so any algebraic operation that you apply to a state or an operator, its basis will kind of track what you're doing. So you can do partial traces, you can do whatever.
There's a question here, why isn't there an autocomplete on the properties? There should be. And I don't know whether Ruhi knows how to do that, how to insert an autocomplete specification, but somebody should show her how to do that.
Yeah.
Was that a yes, or a yes?
Oh, I don't know how, but I'm sure Jose or someone can show me.
Okay. All right. What is random pure?
It's a random pure state.
What the heck do you mean by random? Is it quantum random?
No, it just picks two random complex numbers for the state vector.
Okay. Normalized.
Yes. Yeah. Well. Yeah. All states are automatically normalized.
Okay. And there's a well-defined meaning to random in that case. So you're on the, whatever it is, the block sphere or something.
Right, yeah. Right now, it's equivalent to uniformly sampling from the Riemann sphere.
Okay.
I mean, yeah. We should presumably add ways of modifying the distribution.
Okay.
So that's just showing a basis change, so normally that would happen automatically.
Quantum discrete state. And then you're saying, given this quantum discrete state with this basis, now you wrap quantum discrete state again with and this is the default basis here. Now you give it a specific Pauli X basis, and it generates this quantum discrete state here.
Exactly. And so if you did the same thing now, S is quantum discrete state, and then you did quantum basis computational, it would take you back to the original state vector.
Okay. Okay, random unitary. Quantum discrete operator. So that's a random unitary operator of arity 1.
Yes, and applied to subsystem 1.
I see. That's what that means.
Right. So if you did 1, 2 there, it would be an arity 2 operator applied to subsystems 1 and 2.
Fair enough. Okay, quantum discrete operator in that basis. Can I see what this thing is? If I say
yes, yeah. If you say matrix representation, for instance.
Okay. So that's just a random unitary matrix, you claim.
Yep, that's now been transformed into the Pauli X basis.
And what's the random unitary matrix, and there's some obvious way of doing that. It's obvious what a random S, determinant 1 unitary matrix is. Is that right?
Yes, right. Again, it's basically random sampling from the special unitary group.
Okay. Okay. Fine. I want to see this actually compute something. This is still just bureaucracy.
This framework is primarily bureaucracy.
Well,
this is just showing that your states and operators and things can be in different bases, and it won't care. It will just do the transformation.
So this is an operator applied to that state. It's cool that you can just write this. I mean,
right.
So this is essentially a quantum function. This operator here, O, is essentially like a pure function, a quantum pure function to be applied to a quantum state. Exactly. What is the analog? I mean, if we're to think about this in a little bit more generally, the analog of this idea of a basis, if we think about that in terms of general computation, what on earth is that? I mean, it's kind of almost the data type for that piece of data. That is,
maybe.
I mean, a quantum basis is something where I mean, we don't talk about this even when we do linear algebra. We don't, have this kind of explicit treatment of bases in the same kind of way. Why?
I'd say it's more like an encoding language in the general case.
Yeah, fair enough.
It's giving you the semantic interpretation of whatever appears syntactically in the representation.
Fair enough. I don't have a good understanding though of what that. I mean, because these are in a sense very elementary. I mean, these are like the operations of logic. And I mean, you're like saying, is it a true and false or 0 and 1 to represent logic?
Yes, exactly.
But there's more bureaucracy here because.
Well, because both your functions and your your operands have far more degrees of freedom than they do in, say, Boolean algebras.
Yeah. Okay. Fair enough. Question for our live stream: why are the different colors for the two quantum discrete states here?
Because it got basis changed. So those colors are representations of the complex numbers in the state vector, and so it's just meant to be a quick way of seeing whether a state has changed or not. And so in this case, you can see that its state vector has changed because the bases are now different. So
okay, so there's essentially a color hash of the underlying. I mean, it's probably a complex array plot of the underlying data.
Exactly.
Okay. Measurements. Okay. Okay, we apply a measurement to a state. Wait a minute, why is this data distribution not?
It's a measurement operator. So so a measurement projects onto the eigenspace. So you can now see. So if you look at the eigenvalues of M, it will tell you if you say M eigenvalues. That effectively tells you the possible measurement outcomes. And then the data distribution tells you the statistical distribution. If you apply that measurement a certain number of times, so you could do a random variate now using that data distribution and simulate quantum measurements of that state.
Right. And the cheat for the people who say they have a quantum computer is they just run this under the hood. How would we be able to tell? You're going to show me some kind of, Bell's inequality story here that would allow me to tell. I mean, this is sort of an exercise. If you're, given this formalism, you're saying, how can I tell whether it's running on a classical computer, just an emulation mode with this formalism, versus running on a genuine quantum computer? What's an answer to that? What do I do here to tell whether it's a fake? Isn't it interesting that it's difficult to know?
Yeah, I'm personally convinced you can't.
Yeah, this is kind of interesting. Okay.
This is a ridiculous example, but it's just there to show the generality of the functions.
Quantum basis, it's a product of 3 bases.
Right.
And this now gives us a, okay, well, that's cool. That's
so
nice.
Right, so the example below is showing that actually we can even deal with this crazy situation where you have a composite state consisting of 3 qubits where they're in different bases, and we can still manipulate them and get sensible answers.
Right. Wait a minute. So Frankie here is saying, Frank, I don't know what that, I can't parse the handle here. It's a way to represent a distribution of state information. Which thing here? The data distribution. That's those are the results of measurements. So they are the, yeah.
Right. We mean, in a sense, when we have, so a quantum discrete state can handle density matrices, which you can see if you take a random state and you just trace out a subsystem. And so that, those density matrices are effectively classical distributions of state information, if that's what you're asking.
Okay, what is all this stuff here? So this is just yet more quantum discrete states, quantum tensor product. Okay, I want to see a circuit or something.
Okay, well, we didn't, we could, because we covered quantum circuit in our last meeting, I didn't include I tried to only include new stuff here, but we can talk about circuits later if you want.
I just want to be reminded what that looks like. I mean, do
Sure.
we have the graphics for the circuits now?
Not in this. So I do have a prototype of that, which I can show you, but it's not in this version of the package.
Okay. When do we get sort of final assembly of all those pieces?
Hopefully soon. I mean, I spent last week working on it. I'm hoping to finish it this week or next.
Okay. I don't know what all of this is doing here.
So what we're doing, we're assembling a composite system of 3 qubits, where the innermost qubit is in the computational basis, and the outermost ones are in the Pauli X basis. And then we're showing if we trace out the middle subsystem, we get a composite subsystem which is just in the tensor product of the Pauli X basis, because we traced out the computational basis qubit. And then we're showing that it's the same as if we just took the tensor product of the Pauli X basis with itself.
Okay. This is still very bureaucracy oriented. Okay, great. Show me something that actually computes something. Or is this all bureaucracy in the end?
Well, it depends what you mean by compute something.
Well, like one of these things where we're actually making a non-trivial transformation from one set of gates to another or something.
Well, Ruhi might be able to talk in more detail about those kind of compilation type things.
Okay.
Yeah. We don't have that integrated into the package yet, but I have the function ready.
Okay, it'll be interesting to see that. Okay, wait a minute. This is a comment from SWSH on our live stream. Please consider a framework to work with coordinate-free representations of vectors, spinors, operators, etc. Essentially having an algebra for working naturally with these objects, like what we do for round and complex numbers. Built-in geometric algebra all the way. What does that mean? Does that mean things like exterior calculus and things? What is that?
Yeah, that'll mean representing states in terms of Grassmann algebras and things, which I'm not against, but it's not what we decided to do so far. But we could support that maybe.
Right. So I mean, this is the analog of. Okay, so what we've got here is kind of the explicit. It's like in the case of tensors. This is kind of the explicit tensor version, where the actual, where the Riemann tensor has actual components and things, as opposed to the purely symbolic Riemann tensor that has certain properties. Is that right? Is that the analog?
Yeah, sort of. Yeah, right.
Yeah,
I'm not sure.
So.
Yeah,
I think so. I mean, the comment was referring to geometric algebra, which is a particular way of doing things.
That has what in it?
It's a way in which you add scalars plus vectors, and then you can mix the dot and cross operations.
Okay.
But so it's some sort of alternative way of doing tensor calculus. but yes, so that's separate from what you were talking, which is also true. The idea that rather than having a quantum state with head quantum discrete state, we could have a Q representing, and then you
Yes.
do things with it.
And in terms of, just for my understanding of how things fit together, things like the whole bird track business and so on, and that way of representing, you know, the Roger Penrose notation for tensors and things, how does that fit into all of this?
So that's contraction. So here they have the operation of quantum tensor product, the equivalent of tensor product. And then there is the dotting, which is what those bird tracks represent, the contractions.
Okay, there's a request on our live stream to show the Shor algorithm, which is what I would like to see. And maybe Jonathan, maybe you can just show some circuit stuff just to remind me how that worked.
Sure. I mean, it's so without the rendering, it's not super exciting. But if you just take a bunch of operators, if you want to construct a bunch,
do we have the rendering, or do we have a draft of the rendering, or not?
I have some static pictures. I can see if I can try and recreate them now.
Okay. Did that go through graphic design?
Not yet. No.
Be a good thing to get in there. Yeah.
I'll ask Jeremy. But yes, I mean, if you want to, you can put together some discrete operators and then wrap quantum circuit around it, and it will do the right thing.
Okay, what are we seeing here?
Right. So the basic idea. So Ruhi implemented a couple of different ways of decomposing vectors and operators. So this is so the first example is this Schmitz decomposition. So if we take an arbitrary state or operator, then we can represent it in a diagonalized form in a tensor product of two Hilbert spaces.
Okay.
And so because our basis functionality supports arbitrary tensor product spaces, that means that things like the Schmitz decomposition are really just represented as basis transformations. So the state itself is very nice. It's in this diagonal form, but the reason it's very nice is because we've transformed it into this very ugly basis that you can see as the tensor product of this U basis with a V basis. And so those represent the two constituent Hilbert spaces.
What is this?
So this is now saying, sorry. If you want to see the constituent Hilbert spaces, so by default it will just return the diagonalized state in this new basis. But if you want to see the two Hilbert spaces that we used in constructing that, then you can say give full decomposition true, and it will return the state and these two bases. So those two bases essentially represent those two Hilbert spaces. And if you take the tensor product of them, you get the basis of that qubit, or of that system. Sorry.
Okay. There's our random unitary matrix with taking these two inputs. So it's taking quantum spectral decomposition. What does this mean?
So that's a diagonalization. So it's eigen decomposing that operator, and then again we're showing that that's basically represented as a basis transformation operation. So those are
the bases which diagonalize the operator.
Exactly, right? Exactly. So Ruhi's implemented a couple of these things where we can just take some arbitrary quantum object like a state or an operator and do some decomposition of it purely in terms of basis transformations, which I think is quite neat.
Yeah, that's nice. All right, so then we've got translation from the picture. That's interesting. We don't usually use in our internal strings. We don't usually use non-ASCII, but I don't have a strong opinion about this.
I'm happy to change it back to an O. It would make it easier to do transformations on it.
I'm not sure what the maybe we could ask I would tend to think we should not have the umlaut there.
Sure. In that case, do you want to spell it with the E?
No.
Okay, just to know.
I think so. You could ask Michael if he objects violently to that. I think it's consistent with what we've done in other places.
Sure.
I was just looking at the canonical name of the entity for Erwin Schrodinger. And it doesn't have the E, and it doesn't have the umlaut.
Okay, fine. Okay. All right. Okay, so there's a question about quantum virtual machines. I mean, this is a quantum virtual machine. This is, you can execute things here, right? I mean, the gates can be evaluated.
Right.
The question of whether it is an emulation of a particular machine with particular decoherence times and so on, I don't even think those characteristics are published and well known. That is, you could ask the question, if I feed this thing into manufacturer X's quantum computer, will it actually work, or will the thing just produce, decohered junk? And I would be amazed if that was easy. I mean, that computation is a whole separate computation of which is kind of out of the scope of the quantum computing stuff to understand decoherence, isn't it?
Arguably, yes. Although Ruhi might be able to say something. She's been looking into the possibility of using one-way quantum computing emulation to do things like to simulate error correction and stuff in this framework. I don't know if she has anything to say about that.
Yeah. In that case, we would just have like an initial state and apply a bunch of measurement operators on it. But that can still be done in this framework as well. Like, it just hasn't been packaged nicely, but yeah, that's still a possibility.
Right. So the things for which there exist published specifications, like gate sets, like error correction codes and things, those things we'll be able to support all of them. As you say, Stephen, I mean, like, decoherence times and stuff.
It's hopeless.
I don't think we have.
I don't think anybody. I mean, nobody knows them really.
Right.
And I mean, that's the case where if we were actually running on those machines, we could actually run a bunch of tests, and maybe we could find what is the optimal experimental test that measures, when we get garbage out.
Yeah, using our framework to reverse engineer the decoherence times of.
That's what I'm thinking. Yes. I mean, I don't even know how. I have no idea how they. I mean, it reminds me, when you do semiconductor design, right? You have all these various design rules that tell you, that you won't have too much crosstalk between these two wires if you do this and this. I don't know whether there are similar design, and it's similar to, when you do 3D printing. Like for a bunch of the things we were trying to do with our hypergraphs, printing the hypergraphs, we still haven't managed to print any of those because we keep on getting back errors from the, print vendors saying this thing will not successfully print. It violates the printing design rules. But I don't know whether the quantum emulators are yet implementing things like that. Do you know? In other words, if I say, here's this program I want to run on brand X quantum computer, does it come back and say, sorry, that program isn't going to work properly? Or does it just go right ahead and run it?
I have no idea. Ruhi, do you know?
No, I'm not sure either.
I mean, it's been a really weird thing. I mean, it's been like 5 years now that we've been like, about to run stuff on actual quantum computers, and there's always an excuse why we're not doing it. And it's kind of weird. Right. I mean, this is something, it will be very nice to be able to actually connect this. And I don't know what's happened we've been talking about connecting this framework. And I think the partnerships group has been interacting with some of these companies. I don't really know what the status of that is. Certainly nobody here is dealing with that. Well, okay. So we're looking at more.
I've been copied into a few of the exchanges if you're interested to find out what's happening.
Well, I know there have been active discussions with a bunch of the companies, but I don't know what. I mean, the question is really. Okay, I don't know what any of this is doing. What should I?
Okay, right. So above here, we're just showing that in the Schrodinger representation, when we above on whatever it is 467, we're showing if you apply an operator to an operator or an operator to a measurement, it doesn't evaluate. But if we convert everything into the Heisenberg picture, then now applying operators to states won't evaluate if you run the next line. But
Okay.
applying operators to operators or operators to measurements is absolutely fine.
Well, that's cool.
And in the interaction picture, it's like, it's maximally permissive. You can do anything. Everything is operatable.
And why is the interaction picture not the default?
Because most people both in QM and in QC use the Schrodinger picture.
Okay.
It's currently we're just treating the picture thing as like a kind of sanity check to make sure that you don't do something that you weren't planning to do. Because most of the time, I think if people are thinking in the Schrodinger picture, they don't actually want to apply operators to operators, and they will likely be surprised if that is allowed. We want to make sure that if people do that, they know what they're doing.
Really? I mean, that sounds like type checking, which we generally don't tend to do. But I mean, look, this may be an area where there's enough rampant confusion that it's necessary to do it. Fair enough. I mean, look, it's something people will expect that. So, all right. So, what is this phase space picture? What is
right? So everything we've talked about so far has been in terms of operators on Hilbert space, right?
Yes.
But there is also a perfectly reasonable way of interpreting quantum mechanics in terms of functions on phase space. And so Ruhi has implemented a version of this Vignette transform that allows you to convert between the Hilbert space picture, which is like either in the position basis or the momentum basis, and this phase space picture, which is in both the position and momentum bases. And so if you do the quantum Vignette transform on one of these states, you will get some new thing whose basis you will see is now in the phase space picture.
Okay. And how do let's see, basis element associated. Okay. So what
then
does that mean?
Those are the rank 2 Vignette matrices, the 2x2 Vignette matrices.
I don't know what those are. What are those?
That's the standard basis for the phase space representation.
I really don't like these parens here. What aren't these usually? I mean,
again, those will be subscripted.
Okay.
This is again my own bad typesetting.
What is this? Tell me what this is. Maybe is there other terminology for this? I don't quite know what this is.
I've heard this referred to as the Vignette transform or the phase space transform. I'm not sure if there's another way of talking about it.
But so 0, 0, 0, 1, what does that mean? What do those indices mean?
Those are elements of the the Vignette matrix basis is a matrix of matrices. So those are like the Pauli vector is a vector of matrices.
Oh, and why aren't we representing this as a rank 3 tensor? I mean, just W is
because that's not how quantum basis works. Quantum basis associates a name with an object of arbitrary rank.
Okay, but okay, so what do these indices mean as opposed to the indices inside these matrices?
What indices inside the matrices?
Well, I mean, just the positions inside the matrices.
Well,
refer to the basis here.
Right. So the basis element names are indices in some outer matrix whose elements are themselves 2x2 matrices.
I get it. But
right.
what is the meaning? What is the significance, the interpretation of the outer indices?
That is.
Is one of them some kind of momentum representation, or what?
Yeah, I believe the first number is the position, and then the second is the momentum. And since this is discrete, you can only have like zeros and ones. But normally this is taken in like a continuous space. So then the first one would be the position, but like.
Oh, I know what this is. Okay, I'm just not used to seeing the discrete version of this. Yes, I know what this is now. Okay. But so how would we represent the continuous version of this? I mean, then it's a function. Then this thing here, instead of being an association with discrete elements, will be some function of P and Q.
Yeah, it's an unbounded operator.
A what? Yeah,
it's an unbounded linear operator.
Yes. Yeah, in fact, SWSH on our live stream is asking, what about continuous variable states? Q modes. What is a Q mode? Is that a term that's nowadays a term of art for eigenstates or something? I've not heard it. But then I've been hibernated in this field for probably 40 years. So it might have changed in that time. Who's to know? Okay. Okay. All right. Quantum Hamiltonian operating on this. That's an identity Hamiltonian operating on wire number 1, so to speak. Okay. Parameterized as a function of, wait a minute, parameterized function, what does that even mean? What does that mean? What does this mean?
So Hamiltonian is a general way of representing a matrix that is a function of some parameter, which canonically we interpret as time. So this is a particular shorthand that says the initial matrix is this and the final matrix is that, and smoothly interpolate between the two.
Is that a useful concept? I mean, in terms of Hamiltonians, is that a useful? I mean, I don't know. The time dependent, so a time-dependent Hamiltonian is associated with some external potential of some kind, because otherwise the Hamiltonian is just an intrinsic property of the system, yes?
Right.
So what this is saying is, one could imagine some sort of adiabatic setup where the thing is, slowly turned on and then slowly goes away, which this is not representing. This is representing some interpolation between two Hamiltonians.
Which is equivalent to an adiabatic interpretation.
Is it?
Locally, yeah.
What do you mean? This is a linear interpolation between these two Hamiltonians, right?
Mm-hmm.
I don't understand that. I thought the adiabatic story was at infinity, at plus minus infinity, the thing is 0, and then it takes some value in the intervening time span. But I mean,
right.
Yeah.
Right, but so locally, the adiabatic evolution is sufficiently gradual that it can always be represented as some linear interpolation.
Well, fair enough, but so you're imagining a sequence of linear interpolations here.
Right. I mean, yeah, no one's. This is why the Hamiltonian object, as you see below, has only a limited time domain. No one's claiming that it will be an accurate representation outside of that time domain.
I think this is a little bit bizarre, this use of arrow here, because I think that. In general, one could imagine linear interpolation between these matrices, which is something we don't normally do, right? You could imagine an interpolation, just like we can say, interpolation of, something like this, right? We could imagine an interpolation on matrices as well.
Right.
And that seems like the more natural thing to be representing here. It's an arbitrary. This is essentially
which is what it is. This is as I say, this is a shorthand for representing a linear interpolation between two matrices.
Okay, but what happens if you have 3 matrices?
Well, the shorthand doesn't extend to that case, but
what's the longhand?
Well, to input that as an arbitrary as a function. The Hamiltonian. Quantum Hamiltonian operator contains 2 pieces of information, essentially. Well, up to basis transformation, which is the matrix and the order, just like any other operator.
Yep.
And so the matrix it can be some arbitrary function of this parameter.
So it can be a pure function there.
Yeah. Well, in fact, if you look at the matrix representation, you'll see that it is.
Oh, I see. Cool. Oh, that's cool. All right. Okay. That's nice. All right, fair enough. If this is useful, I just don't, interpolating from one Hamiltonian to another, I just don't know whether that's the right thing. Okay. Eigenvalues as a function of time.
Right.
That's when the eigenvalues are closest, is that right?
Mm-hmm.
Okay, this is. Show me, can I plot this?
Again, in Ruhi's implementation, you can. I have not yet integrated that into the rest of the design, but
okay.
She has a version of this that will essentially plot the norm squared.
It'll make a big version of this.
Exactly.
Why are we plotting norm squared? Why aren't we using some of our technology from complex plot to show both the abs and the arg? Why don't we just use what we did in complex plot? I mean, so in other words, if we what's a good example here? Wait a minute.
Think you need complex numbers?
What's that?
Complex numbers in the limits?
No, but I thought I was trying to plot this. Oh, this is, oh gosh, I get this wrong every time. What I meant was re-im plot. But actually, I don't want that. I want abs-arg plot. Right. That's the type of thing.
Which, I mean, if you want to do that in this case, you can. If you
using abs-arg or something else.
Yeah, if you do abs-arg plot of e of x and then call state vector, and then have x go from 0 to 1.
What do you mean by of state vector?
Yeah, so e of x is going to return a quantum discrete state, so then you have to request its state vector. And I don't know if you want to plot all of the components or just the first component or something.
Plot all the components. X
from 0 to 1. And you might have to specify in jumps of 0.01, which I think is the default, but maybe not.
This has just gone crazy here. Don't I have to say 0.01? Well, if I evaluate this, it's probably going to help. Something went wrong here. Oh, that's not what I can do.
Well, that's a big version of the plot you saw above.
It is, but it's kind of, but except that it also has the arg information as well as the abs information. I think this is a nice default for these because it's going to give the phase.
Right.
Okay. What is all this stuff here? Okay, that's a more elaborate. Okay, that's from a random unitary operator. I see. So if I did the analogous thing here,
you need to say matrix representation.
Oh, instead of state vector.
Right.
Okay, that's cool. So that's the applying a random unitary matrix as the evolution operator.
Yeah, well, I mean, in this case, it's not. No. So the evolution, okay, the Hamiltonian is not random. The Hamiltonian is still the thing we defined above.
Yes.
What we're doing is we're applying that Hamiltonian to an operator in the Heisenberg representation.
Fair enough. Okay. We should make that a spelling word, by the way. All right. So, okay. So I think I understand what this is doing. Cool. But everybody on the live stream and I are asking for a few real examples. Do we have that?
Real examples meaning?
Non-trivial algorithms, quantum algorithms.
I think Ruhi has some example cases. I don't have them implemented yet. But
can you either send them to me or do you want to share your screen and show them?
I have Grover's algorithm implemented.
Can you send that or show it? Which one?
I can. Oh, it might take a while. I'll have to clean it up though. So.
Okay. You know, we really, everybody on this live stream is asking for real examples, and that's what I want to see too, because that's what's really going to, I mean, we've done this in the past of generating real examples. We should have all of the standard algorithms implemented in this framework, which should be very easy. I mean, you know, we've been spending a lot of effort to build a very clean framework. I think we have that. The proof of that is, can we implement all the standard algorithms in a nice, clean way? And I think the answer is yes, but we should actually do it.
Right. I mean, as I say, we have we have those. It's just that they don't happen to be implemented in this version of the package because I've been mostly focusing on getting the design correct.
Fair enough. Okay. So, all right. So what else do we need to make sure to achieve right here?
Right. So the main thing that I wanted to get insight on, and again, Ruhi knows more about this side of it than I do, is exactly what we're going to do with respect to compilation. So right now we have this framework where most of our compilation functions have an external dependency on this universal qcompile framework.
Okay.
And we need to figure out exactly what we're going to do with respect to that.
I'm sorry, I don't understand. So the compilation, we have these tabular data of what what gates different people's computers support.
Yeah. I mean, so all of that is fine. The problem is, how do we do this essentially arbitrary precision matrix factorization problem, right? So if you give me a quantum circuit and some epsilon, and you want me, and a list of gates, and you want me to come up with a composition of gates that approximates that circuit to within epsilon, right?
Okay.
And that's in general an algorithmically complicated problem.
Okay, so there's probably a tolerance option. I mean, that would be the standard thing we do in linear algebra, is give a tolerance option to specify that epsilon.
Sure. Yeah, that's fine. And then we can have some reasonable default. So the point is, in order to solve that problem, there is this package written in Wolfram Language called Universal qcompile that Ruhi has managed to essentially write an interface for within our framework. So we can do those compilations, but it requires this external package, and we don't know exactly how to.
Different. Well, we should obviously talk to the people who wrote the external package and figure out what the best way to deal with that is.
I emailed the lead author of the paper, and they didn't reply, but I will email them again.
That's a very practical problem. I'm sure we can solve that problem, and I think that's the right that's the right place to solve that problem. That problem is not a technical problem. That problem is purely what would they like to do? Should we store are they going to maintain the thing? Should we store it somewhere in our framework? Should we get releases from them? How should that work? But I mean, as I understand it, those are the algorithms that are doing the compilation to a particular gate set. Is that correct?
Exactly. And so then we'll pick some list of gate sets that we want to be able to support, and obviously have the ability for users to define their own, and then we'll just interface with their framework.
And effectively what this is it's trying to decompose a matrix into some product of other matrices. Is that correct?
Exactly. It's a matrix. It's a generalized matrix factorization problem. But it gets a bit complicated.
Is that a function that we should have in at least the function repository, if not the system? Matrix factorization. Isn't there so this is saying, okay, this is kind of an analog. Okay, let me just see if I understand. I mean, this is kind of like a word problem type question, like the word problem for groups. You've got a certain set of generators, so to speak, and you're asking the question, to a certain precision, can I approximate this element of what's effectively a Lie group by some product of generators? Is that right?
You've developed such an automated theorem proving mindset since the physics project started. I like it.
Well, okay, fair enough.
But yes, it's a similar sort of thing. It's like solving an approximate word problem for some continuous group.
Of course, that our inverse problem of being able to deduce the effective local gauge group is similar to that.
Yep.
Interesting. So I see, but in this case, you're given the group. You're told these are the generators that we want to use. I mean, the group is basically SU2. Is that true?
Right. Well, yeah, for qubits.
Right. Or SUN in general for n qubits. And then you're asked, this is a set of generators, and each of these bases is essentially a set of generators for that group.
Right.
Is that correct? And it's a much more, I mean, in a sense, it's a great sort of Cambrian explosion of possible, sets of generators, because probably people haven't considered such a diversity of sets of generators before. But okay, given a set of generators, you are trying to find a decomposition of essentially a quotes word, and you're trying to find a representation of an element of the group as a word in terms of those generators.
Right.
Right. And the claim is that that is doable even in a discrete group. That would be, a potentially unsolvable word problem. Is the claim that in a continuous group that is a readily approximable thing? And
yes, right. So because you can apply variational methods, in a sense, you don't get so bitten by the undecidability of the word problem.
Right. Well, I mean, like most of these things, people, there is a belief, at least, that you can get approximations without running into undecidability. May or may not be. I mean, look, in the case of, there might also be a result, like there is for real algebra as compared to integer algebra, that, in the case of real numbers, everything is decidable. That's the Tarski business. Whereas in the case of integers and Diophantine equations, it's not decidable. Is the same thing true for finding approximating elements of Lie groups, I wonder?
I'm sure presumably that Turing paper you forwarded me a few weeks ago must have said. I didn't get around to reading it yet, but must have said.
What was that? The Turing paper was about
discrete approximability of Lie groups,
in which Alan Turing concluded that there was no way to do it.
Right. But I'm sure he must have made some claim about decidability. He was Turing, after all.
Yes, but he compartmentalized, I think.
Oh, okay. That's disappointing.
We can look it up. Let's look it up. I'm curious about that. Let me just look. I wonder whether I put that in my collection here. Unless you can forward it back to me. Let me take a look.
I can, if you.
I don't seem to have put it in my. I obviously didn't think it was relevant enough. Let's see. It was like the first link for approximation of Lie groups by discrete.
You say discrete is discrete and still infinite, right?
In general, yeah.
Because once you go to finite groups, this is always solvable.
Sure. Yeah, we're talking about. No, we're talking about the word problem for infinite. Okay, I've got it in the Turing archive has this. It has been shown by J. von Neumann that with okay. Let's see, how do I, to go to full screen, click the little button that says this above. Oh boy, you need to install Adobe Flash Player. My computer probably isn't capable of doing that now. Okay, that works. 1937. So that's right after Turing machines. Let's see how much he believed in Turing machines at that point.
Yeah, surely undecidability must have been fresh in his mind.
Yes, but I'm telling you, he compartmentalized. And when he went to Princeton, which I think is where he wrote this, I mean, he was working with Church, and he thought he was doing algebra again or something. Okay, wait a minute. View all documents in. Oh,
I've just sent you a PDF. Oh, well, I've just put a PDF in chat. Oh, do you want me to email you a PDF?
I think you need to email me this PDF. Okay, but people are still asking for Grover's algorithm. So Ruhi, if you have a chance to produce that, that would be good here.
Yeah, Ruhi, can you share screen?
Yeah, I can share screen.
Okay.
Are you ready to show that algorithm? I still just want to look at this for a second.
Yeah, sure. Whenever you're done, yeah, let me know.
Okay. I don't know what he's doing here. There's no decidability in sight. Those are random characters of groups. An approximal Lie group. Yeah.
This paper looks a lot more boring than I gave it credit for. Never mind.
I think it is quite boring. Yes, I think it's quite. I mean, it's basically look. It just ends. It just ends, and there's no decidability. I mean, it's kind of funny because I think within that exact same period of time, he was working on the word problem for groups.
Mm-hmm.
I think this was him trying to fill out a footnote, and anyway, so I think the conclusion of this paper is there isn't a good way to find systematic approximations to Lie groups. Although I think we need to find one for the thing we're doing, and I think, in fact, that idea of mine is not completely crazy for doing it. Okay. Anyway, that was a sideshow. Okay. Let's okay, Ruhi, ready to share your screen? Let me let you do that. Go ahead.
All right. Okay, so as we saw, like the quantum Hamiltonian and quantum evolution functions earlier.
Okay, so wait a minute. Quantum evolution, Grover. So what is this doing here?
So pretty much eventually we hope to have like certain named algorithms in the framework itself. So right now I'm just showing like the underworking of the algorithm. So for example, if you had
this is how you would write down Grover's algorithm. That is the Hamiltonian for Grover's algorithm, is that product. That's pretty nice.
Yeah, and then
that's really quite nice. Okay, go ahead. Yeah.
And you can start with let's say 1, 0, and usually what Grover does is it takes like this maximally entangled state, and then it takes it into like whatever you're looking for, which is 1, 0 in this case.
Okay.
So you can
show us this for a higher value of n. What value of n are you using here?
Here it's just 1 because there's only 1 qubit, but
okay.
Yeah, for 2 qubits, yeah, you can see a similar thing.
Okay, just to impress us, do it for like 8 qubits or something. And can you?
Yeah, I can try.
We could just copy your input from above, but anyway, whatever.
Yeah.
Okay. So now what you want here is, I would think you want to just say append to table of 0,7 a 1.
If I have 8 qubits, I'll have 2 to the power of 8 things.
Right. Does this work if you just apply it to random states?
No, because Grover finds something in the computational basis. Like it ends
What's wrong with having 2 to the 8?
Right.
Doesn't sound too bad. Well, okay. All right. Let's make it easier for you. Let's no. Oh, you want 2 to the 8? Oh no. Okay. Let's have fewer than that. Let's just have 2 to the 3 for now. You want 0, 2. You want 0, 2 to the 3 minus 1.
Oh, right.
Okay. Yeah, I'm glad you didn't do an 8 there. Now, what's it doing? Why is it taking so? Okay, fine. Now let's just copy that list plot thing.
Mm-hmm.
Okay, what is this showing? So as a function, what's on the x-axis? Go ahead.
It's time, I guess, since we're evolving a Hamiltonian, and then on the y-axis, it's the amplitudes, like from the initially like entangled state, like what happens to the probability amplitudes.
So wait a minute. So what this is saying is it is successfully searching for. Can you actually explain what's really going on here? I mean, so in this algorithm, what are you feeding it as input? What?
We start with a maximally entangled state, so that's essentially the input for Grover.
Okay, so that's the quantum discrete state that you've been giving there. So you could give a
Mhm.
random quantum discrete state, presumably, as well. Is that right?
Mhm.
Let's
Yes,
see that.
but I'm not sure if it'll end up where we
If
want.
you list random pure, comma 3.
Okay, and so what this is doing, what does it have to do? Is it ultimately solving differential equations, or is it solving what is it ultimately doing here?
It's it's evolving the state according to Hamiltonian.
So that's solving Schrodinger's equation. Is that true?
Yeah. Mm-hmm.
Okay.
Pretty much.
Is it doing that by taking matrix exponentials, or is it doing that by solving it with differential equation solving?
It's using desolve or NDsolve depending on what it can. Okay.
No.
Okay.
Yeah, don't give up yet. There, we got a result. Okay.
No, we didn't.
I just clicked on it.
Oh. Why is it taking so long? How many equations are there here?
8. So.
Okay. Someone's asking, can we explain what's going on? Okay, we're trying to show an emulation of a quantum algorithm, specifically Grover's algorithm, which is a search algorithm. But maybe you can explain it, because I'm trying to understand also what's going on here. So we start off with an initial quantum state, and then this on the x-axis is showing the time evolution of a quantum computer. Is that a fair assessment? Okay,
Mhm.
now plot that. You've got a result there. Okay, now you're going to explain what the heck this is.
Okay, so our state that we started with here, okay, I don't think I'll be able to get it back, but ideally, these are the amplitudes of this initial state that we started with.
Why are they on the right? Why are the amplitudes on the right?
Because we started, so Grover takes like an initial maximally entangled state, and then it's supposed to technically find this state that we put in. This is the one we want to find. And then
what does it mean to find a state?
It gets there, I guess.
But wait a second. Mm-hmm. At the initial state, it's maximally entangled in the sense that if we look at our representation of the state, it will have a bunch of off-diagonal things and so on. Is that right?
No, I think maximally entangled is probably the wrong word to use. They're all like equal probabilities. Like each basis state is an equal probability. That's why they're all like starting at one point.
Okay, fine. Mm-hmm. And then what it is doing is taking all those basis states and doing what to them?
It's applying like the Grover Hamiltonian, which
and what does that achieve?
It'll evolve that initial thing into what we want to like.
But what is the objective? What is the algorithm trying to do? I thought it was a search algorithm.
Yeah, so it's kind of like finding this thing from.
What does it mean to find it? I mean,
sorry, can I mention something?
Yeah, go ahead.
Yes. Yeah, so the basic idea is you have a black box function, and that function has some unique input. And then the question is, can you work out what that unique input is by only evaluating the function of order like square root n times? That's the problem that Grover is trying to solve.
Can you explain that in the context of this picture?
Yeah. So the what Ruhi was describing as the maximally entangled state is essentially like, I think my way of thinking of it is it's the minimal information state, right? The state that minimizes Shannon entropy or von Neumann entropy is one where effectively you have equal probability of every basis state. Right.
Or equal amplitude of every basis state. Which?
Well, equal amplitude in this case. Yeah, equal amplitude, sorry. Equal probability amplitude, yes. And then, yeah, so from the state of having minimal information, for having minimal entropy, you're then trying to work out what the unique input for that black box function was.
What do you mean the input for the black box function? I don't understand. I mean, so this is turning each state into having a distinct amplitude on the right. The y-axis is the magnitude of the amplitude. Is that correct?
Yeah, it's the norm squared of the amplitude.
Mm-hmm.
Or the norm of the amplitude. It's the abs probably of the amplitude.
No, it's a probability, so it's the norm squared.
Okay. All right. Okay. So this is, so along this thing, it's effectively measuring, we're showing what the result of a measurement would be as a function of time for each of those basis states. Is that correct?
Yes, you could think of it that way. Yeah, yeah. If you were to project along each basis axis, so to speak, that's what that. Yeah, that's what you'd see. That's what those are the probability. That's the probability.
So what is this algorithm really achieving? I mean, if I were going to practically use it inside my, computation, what would it actually do for me?
Tell you the input for your black box function.
Wait a minute. So, and how is it telling me the input? How do I read out the output here?
Well, those probabilities that is the probability distribution of the input pure state. I mean, I don't think it is in this case because it looks like that algorithm isn't converging. But in the cases above where it did converge, you can see it's converging to a 1-0 thing, which is the input.
No, in this case, our initial state was random, so it's converging to like whatever this was.
Right, but the gradients of those lines don't look convergent.
Yeah.
At least in that number of steps.
No.
Whereas the ones above definitely do, and they look like they're converging to 1 and 0, which is what you'd expect.
So that's interesting. I mean, so if we think about this just in terms of the life of the quantum computer, right? The convergence time here, this is yet a different thing. It has nothing to do with decoherence. It's purely how long it takes in a sort of, I don't know, Fermi pasta Ulam kind of way to converge to a certain, so the claim is going to be that in the end, this is going to sort of, I don't know how you stop it at 300 steps above there. Why did it stop there? If you'd kept on evolving, would the thing have sat at a 0 and 1 in line 105 there? Here.
Yeah, I believe so, yes.
Well, it's converged on the input state, so yes.
Right, but I understand. But how do you, in your quantum evolution thing up there, where do you give the time parameter that says how much?
It's in the, so since this was like a named thing, it's implicitly said in here. So ideally the time is this.
I see. So if you change that to twice the time, okay. So the argument then is, the claim is that for a Grover algorithm with n inputs, it should take pi square root of n over 2 time to converge. But yet, in the example you gave down there, it didn't converge after that number of steps.
This might just be for computational basis states and not like random things. That's why it didn't converge, maybe.
Yeah. I'm very suspicious always about these quantum algorithms, about whether they're really actually going to work. And that's another, I mean, well, that'd be interesting to know how long it actually does take to converge. I mean, can we just try, just try one more thing. Try for a state vector. Well, here, you can change that. Yeah, I mean, you could change that to some different value, but let's, rather than waiting for a really long time for the 8 case, let's try the case of, let's try the 2 case, for example. Just try that case that you have above and start it off from a random, well, here, don't mess up this.
Oh, okay.
Let's yeah, just make a copy of that and let's try. Okay, whatever you want to change that.
Okay.
Whatever. Do comma 2 there. Okay, now we're going to really do the Grover algorithm, because the Grover algorithm is supposed to be telling us, we're going to be actually trying to use Grover to deduce what the initial state was, which we don't already know here, right? Because you didn't store what quantum discrete state is here, we actually have to use the Grover algorithm to figure out what it was. Okay, so it hasn't converged here, so run it longer. So can you change quantum evolution? Just copy down the complete form that you have there. I don't know how you're going to do this, but however you want to do it, but just run the thing for twice the time.
Okay. I'll just.
Let me wait, but.
Oh, there we go.
Oh, but it's a different state. Hey, look, just say QS equals and then some, that's that random state. Grind. Okay. See, it's really a shame that no, look at that crazy thing. Look at it. It didn't converge. Okay, so try running it like, twice as long again. For that same state.
Mm-hmm.
So, it's very bizarre. This quantum algorithm basically doesn't tell you when it's finished.
Okay.
Well, you can determine to some arbitrary probability that it's converged.
What the heck happened there? It's a recurrence. Right? I mean,
these are periodic functions. That's why the domain is pi square root n over 2, is because if it hasn't converged in that time, because it's a periodic function, it won't converge.
Okay, but the advertised purpose of Grover's algorithm, it is one of the 2 headline quantum algorithms that's supposed to work, right? So far, this is making an unconvincing case to me that Grover's algorithm actually works. What went wrong?
I think it has to do with the initial state. Like your initial black box state, I think has to be in the computational basis, not random. Like it can be any one of the computational basis states, but
of which there are 2 in this case.
Yeah, for 1 qubit, there's 2. Yeah. For 2, there will be 4, and then so on.
Okay, so then what you're saying is, what a weird thing. I mean, okay. So by the way, for the Shor algorithm, have you tried implementing that or not?
No, not yet.
But it should be straightforward, right? Just to show us again the implementation of the Grover algorithm at the top here.
Okay.
I mean, that's pretty nice, actually. It's really quite nice. It's very direct. It's cool.
So again, maybe I've misunderstood the Grover algorithm, but I don't think it requires this input state for the function to be in the computational basis. It just requires certain orthogonality conditions to ensure invertibility, which aren't guaranteed for a random state.
Maybe we just have some basis issues then in the Hamiltonian.
Right. But I think it should be possible to construct some sum of orthogonal states that aren't necessarily in the computational basis. They're not aligned with the computational basis elements, but they're still mutually orthogonal. And that also should be an invertible input.
All right. So project for Ruhi is make a more convincing demonstration of the Grover algorithm.
Yes.
Convince us that the Grover algorithm is actually useful for something.
Okay. Or invent a better one.
What's that? Or invent a better one. That would be fine too. I mean, But so just to understand, okay, so if we were doing this with Shor's algorithm, what we should see is you put in some representation of an integer, and out comes a representation of the factors of that integer. Is that correct? And what we will see, go ahead.
In that case, it won't be like with evolution and Hamiltonians, but it'll probably be with quantum discrete operator, and then it'll just be a circuit.
Okay. So I actually thought, and maybe I'm just confused, I thought the Grover algorithm was a circuit algorithm too. I guess I'm confused. Is it not? Is it a continuous time algorithm?
It is, but this was just a continuous time example of it. Like it can also be implemented like this.
Well, can Shor's algorithm also be? Surely Shor's algorithm, any circuit also solves the continuous time Schrodinger equation, does it?
Yes, that's true.
So we should be able to see the evolution of the Shor Hamiltonian, basically.
Yeah, probably.
That will be very interesting to see. Go ahead.
The problem with representing, I don't know about with Shor's algorithm, I suspect it's the same, but with Grover's algorithm, the circuit representation is the size of the circuit representation is itself a function of n. The number of gates you need grows like on the order of square root n, I believe.
Where n is what?
Where n is the size of the number of subsystems in the input.
That's freaking crazy. I mean, I'm sorry. I'm just
not really, because we have to. The point is that you have to evolve the thing, as I say, for order square root n function evaluations.
No, I know, but by the time you've got your circuit, you've burnt your circuit in at square root of n size, and you're doing square root of n function evaluations. What are you gaining? You're trying to do a search over n things.
Function evaluations are the order square root n gates. That's why you need order square root n gates.
So the claim is you're encoding what would otherwise be an order n search in hard circuitry of order square root of n size.
Precisely. That's the theoretical speed up.
But in our case, when we're seeing it as a continuous time thing, so what happens between those gates? So the claim is that those gates all sort of come to equilibrium fast enough, because obviously you're clocking the thing in some way, and it's actually satisfying the continuous time Schrodinger equation between each of those gatings of the gates, so to speak.
Yes, right. If you did a sort of linear interpolation between the operators that correspond to each gate.
I understand, but what is the guarantee that the system has actually reached the sort of equilibrium state when the next gate is being executed? Because that's what's not happening here. I mean, if you go down to those other pictures, here it's still flapping around. It didn't reach, in that top picture, it had reached some kind of equilibrium where it had successfully untangled itself. But that isn't happening in the other cases.
And the same thing would happen like this. I don't see. Maybe I don't understand your question. I mean, the same thing would happen in the circuit representation.
In principle, yes. In principle, what would happen is in the circuit representation, you would see the continuous time thing. Then it would say, okay, right, the next clock pulse has come through. I'm going to go and run the next gate. But between the first gate running and the second gate running, it would have gone to something which has essentially gone to equilibrium, where these curves of amplitude as a function of time or probability as a function of time have gotten to zero derivative, correct?
I'm completely confused by what you're saying. The circuit representation would be each gate, the input state would be effectively some uniform sample in time of this representation here. There's no convergence required between gates.
Well, you're saying, I see. You're saying because what you're showing here is the measurement is what you would get if you stopped it after 100 time steps and then measured it. That's what this picture is, as a function of where you
exactly.
stopped it. Right. So it's like running a whole ensemble and then stopping it and doing a measurement at every point in the ensemble. So you could do the exact same thing with the gates, couldn't you?
If you measured the state in some intermediate, before it had completed the circuit. Yeah, right. But that's nothing to do with convergence of states between circuit elements. I mean, what would happen is
yeah, go ahead.
If you had a circuit of size 100 that was implementing this algorithm, the inputs for each of those gates would be what you'd get if you just took this plot and then sampled it at uniformly at 100 points.
Yeah, I agree, because it's not this plot, it's a different plot that is the thing that corresponds to this evolution of the Hamiltonian that represents those 100 gates.
Right.
But the point that I'm making is, if it is, this is an indicator of whether the thing, I mean, there must come a point where you are trying to clock the system so fast that your Hamiltonian is not successfully, what am I trying to say? Okay, if you clock the system too fast, how to say it? The intuitive physics would be that the gate, you're pushing things through the system so fast, you've got so much of a force of pushing things through that's a big energy, a big piece of Hamiltonian that's pushing things through, and that would end up dominating the energy differences and the pieces of Hamiltonian associated with each gate. And the gate would not have a chance to sort of apply its full effect on the probability amplitude. Does that make any sense? Look, there's clearly an upper limit to the speed that, in terms of the time. Okay, how long does it take to execute one cycle of Shor's algorithm? Okay, you're factoring 15. How long does that take? It isn't instantaneous. It's something where you have, just like in your plot here, it takes a certain number of time steps, certain number of time units to get that factorization done.
Sure.
Okay, how many time steps is that? Or how many time units is that? and what is it a function of?
Are you trying to push towards some Zeno type thing?
Yes, I am.
Okay, yeah. I mean, at the very least, we can compute a lower bound based on Zeno.
Yeah.
We know if you punctuate a unit interval with uniform measurements, we know how the slowdown works.
So why do we believe these algorithms actually work? I mean, in an actual quantum computer, there's got to be an upper limit for a given quantum computer. There's got to be an upper limit to how fast you can expect Shor's algorithm to run.
This is actually an interesting question. Give me like 2 minutes. I'm going to try and compute it.
Okay, fair enough. Yeah, okay. All right, let's see. Is there anything else we have to cover in terms of, so the roadmap here for what we're doing? I mean, we've got to integrate the circuit stuff. We probably wait for Jonathan to compute his bound on the speed of Shor's algorithm. I'm going to be very impressed if he can, and he's going to then show us his handwritten computation.
That's okay. That's okay. I'm still listening.
Okay. Well, okay, so we've got the circuit stuff to integrate. We've got these sample algorithms to show. We've got figuring out the details of how we do the compilation. And then hopefully, in a pretty short time, we'll be ready to release some version of this package, yes? What's the state of documentation?
It's like almost done.
Wow. You mean there are function pages for every one of these functions?
Yes, yes.
With actually, Ruhi, can you show some examples?
Sure. I'll probably have to. Okay, I have several. I guess I could show discrete state first.
Okay.
Yeah.
Cool. Scroll down.
The examples probably won't work right now, but after the package is cleaned up.
Yeah, I don't think that's that needs thing is not the right way. I mean, I understand that's what you need to do for this, but I don't think that's the way we will want to document this as a Packlet. And that's a good question. I don't think we yet have a standard for how to do that for the Packlet repository. Jose, do you know anything about how that should be done?
So I did suggest using needs, and I think for packages is what we do. Now, how we are going to handle it via the Packlet repository, I don't know.
Let's put that in the next meeting about the Packlet repository, because this is a good question. I don't think we know the answer to that. Okay, that's cool. Can you scroll down here? The thumb is not that far down. So.
Oh.
No, that's okay. I'm just scroll down on this page. Okay, cool.
Yeah.
Great.
Okay.
Okay, good sample. All right, did Jonathan finish his calculation?
Oh, I'll stop my screen if that is okay.
Yeah.
I have a bound, but it's not very good. We can talk about it later.
What do you think your bound is in terms of maximum entanglement speeds of large numbers of solar masses per whatever, I suspect.
Yeah, it involves upsilon.
Yeah, it's bad. But more seriously, I mean, so the basic point here is there's got to be, I mean, there's got to be an upper bound on how fast. What is it determined by? What is the scale? What determines the scale for the speed at which you can run a quantum algorithm like this? What determines the speed that you can basically sort of send qubits through a quantum circuit?
Yeah.
I think what it's determined by is, oh gosh, this is giving me a flashback to when I worked on this stuff in 1980. okay, what we figured out back then was it all had to do with energy differences between states. And the claim was, I mean, this has all been washed away in the theory of quantum computers, and I think people have completely ignored this issue. But as I remember because I even remember working that out by basically looking at eigenstates of various Hamiltonians for spin chains. That the issue is, if you have a quantum circuit, so to speak, and it has a certain, and you have states whose energy difference, given that Hamiltonian for the whole quantum circuit, you can look at the possible eigenstates of that Hamiltonian, and they have certain energy differences. I think the point was, imagine that those energy differences, what happens if those energy differences are incredibly close together? How do you resolve which state you're in, so to speak? Did that make any sense?
Right,
I mean,
right.
The thing is ultimately just some Hamiltonian.
But eventually the differences become small enough that they slip through your net.
Right, and the claim, I mean, in Dick Feynman and my efforts to do this in like 1980 or 1981 or whenever it was, the thing that seemed to be the case was, as soon as you were trying to do a non-trivial computation, you got these small energy differences, and the time necessary to get the result was determined by some time to resolve that energy difference, which was long, otherwise known as you can't measure it fast enough. If it was a computation that was non-trivial, the measurement will take a long time. I don't know. I mean, I'm a little surprised that I haven't seen pictures of kind of like the continuous time version of Shor's algorithm. I've never seen such a picture. Why? I mean, it must be the case in an actual, physical instantiation of a quantum computer that happens. I mean, you get some number of outputs, and they each take a certain amount of time. They don't take zero time to compute.
Right.
Well, okay. I'm still confused as I was 40 years ago. So that's some.
But I suspect that the small energy difference thing might end up being equivalent to this Zeno thing.
I think it might be, yes.
You end up getting you have a square root n speed up of the quantum algorithm, but the change in the survival probability as you uniformly sample the interval grows like an exponent in n, I think. And so eventually, the exponent in n is going to overtake the square root n, and then you lose advantage.
Yeah. Oh well. Okay. Something I was asking on the live stream, the packages for modeling quantum systems with discrete states. Yes, that's correct. And the idea is to make it more general than just being able to do quantum computing, to be able to do more general quantum discrete states with the hope that it will eventually kind of connect up with our chemistry system and so on. Okay. Well, all right. Very good. All right. Well, we should probably end here, and good stuff. Anything else we should make sure to cover right now?
I have one comment for you to ponder.
Yes.
The difference between discrete operators and measurement operators is that one acts between hypersurfaces and the other acts on hypersurfaces in a multi-way evolution graph.
Say that again.
So the discrete operators are the edges connecting neighboring hypersurfaces.
Yes.
And the measurement operators are edges connecting states on the same hypersurface, i.e. resulting
That's interesting.
in branchial collapse.
Yeah. I understand.
Which it was a connection I hadn't really made until I started working on this framework again. I was like trying to work out what exactly the difference between the discrete operator and a measurement operator is, and that's it, I think.
That's very cool.
They're rotated versions of the same thing.
Yeah. I understand. That's very cool. And we really need to explain to people on the live stream what the heck we're talking about. And unfortunately, how many pages do we have of explanation of this physics project now? It's about 800 of my pages. And how many of your pages?
About 150, 200, yeah.
Okay, so we've got approximately 1,000 pages of explanation of what the heck we're talking about, which we very, very much hope we will be able to release into the wild within the next few weeks. That's a very interesting observation. Okay, I'm really looking forward to yeah, I'm looking forward to us being able to really talk about physics on these live streams. Somebody is asking, how many qubits will quantum computers need to have to be viable for machine learning applications? When will that be achieved? You know, the machine learning cases are things like the D-Wave computer, which is really more like a quantum spin glass than it is like one of these circuit type computers. And I think you can potentially achieve reasonable things for solving optimization problems or solving, machine learning training problems with that. I think that's really an orthogonal problem. I don't know if Jonathan or Ruhi has a different point of view about that, but to me, that's a somewhat different formalism and different problem than this. I mean, one of our hopes here of a couple of years ago was to be able to sort of define what it means to have a quantum, actually exactly 2 years ago, for a reason that I can show you, to define a quantum neural net in a circuit kind of way. Let me show you something here. Where is it? Let me look here. It's odd. Let me see here. Where is this? I am looking for something. Hold on. Sorry. Oh, here we go. Wow, look at that. It was exactly 2 years ago, because it was April 1st of 2018 that I wrote this crazy blog post that was kind of fun about quantum neural blockchain AIs, which was given that buzzword, what could it possibly mean? And actually, it means something quite interesting, because actually the physics of what's going on in those different cases is surprisingly analogous. Okay. All right, let's see, we should wrap up here. Just a reminder, somebody's saying we need I really want to release this physics project. It's just, if this virus hadn't taken over the world, we would have already released it. Very frustrating. That's certainly not the only reason. I can't claim that is the most serious problem in the world as a result of the virus, but in our little micro corner, that is a frustrating thing. A comment about live streams. People are interested. I mean, tomorrow I'm going to be doing a very different live stream aimed at kids who are currently stranded without school. I am going to try and do a fun with math live stream aimed at, what are we saying, like 10 to 14-year-olds? Although I think it will probably have some stuff that is at least not well known to grown-ups, so to speak, although I haven't quite figured out what I'm going to talk about. But it should be accessible to anybody with a reasonable knowledge of arithmetic. But it will probably also, no doubt we'll be talking about undecidable problems in math, but perhaps not under that name. All right, well, great. Good stuff, Jonathan, Ruhi. The package is looking nice. Let's get it finished. And thanks to everybody for joining the live stream.